Hello everyone, welcome to week 6. This week we're going to be adding frame buffer functionality into our OpenGL framework, and at the end we're going to also implement our first post-processing effect. And I'm really excited for this week. This week is really the last week where we have to code directly into our framework setup. After this we'll be able to just shoot out post-processing effects 1 week at a time. So I've been really excited to reach this point of the course because after watching this video, you can officially call yourself an unofficial ME-approved intermediate graphics programmer as opposed to a beginner programmer. And I say that because frame buffer objects are really where graphics programming explodes and becomes, fulfills its full potential. So let's dig in and see what we can do. First thing I want to do before starting is to go into the game class and to take a look at this line, enable texture 2D. It was my mistake for including this, and it's safe for us to remove it. GL enable texture 2D is actually deprecated functionality that used to be useful when textures were handled much more closely to OpenGL's side of the job instead of our job. But at this point, we have full visibility of textures. We're binding them to shaders ourselves. We're using them in our shaders manually. And this call actually doesn't do anything anymore. So we can remove that. If you were using GL get error, you would actually observe that an error would be thrown after that function call because it's ignored. It's not even valid anymore. So just to prove to you that it does still work, let's give it a run. And we'll still see the grass texture, just as we did before. But for those of you that have enable and disable texture 2D all over the place, feel free to remove those, and you're good to go. So let's get into the meat of things. First things first, as usual, we're going to add a new item into the header files. Let's call this frame buffer.h. Pragma once is muscle memory at this point. We're going to need some GL stuff as well, so we're going to include glue.h to give us access to that. Let's open up a new class, frame buffer. Public and private spaces. So before I open up the first constructor, I want to talk about how this class is going to be used. And keep in mind that frame buffers can have only one depth texture, but they can have multiple color textures. And it's really difficult in one function call to initialize the data for a variable amount of color textures. So instead of having one function call try to initialize this entire class as we did with shaders and textures and meshes, instead what we're going to do is we're going to have the constructor take an integer representing the amount of color attachments that this class should expect to have. And then after the constructor takes that, it can allocate the right amount of space. Then the user can simply call the init color texture function one at a time for the amount of color textures that they want, and we'll see how we'll set that up. So like I said, the first thing we're going to need is to specify the amount of color attachments in the frame buffer constructor. And then let's create a destructor. Now here's the issue. C++ is going to complain to us that it wants a default constructor that doesn't have any arguments, but we actually don't want to use it. We don't want to explicitly set it either. So what's the solution? The solution would have been normally to do this and maybe throw some kind of error in there, but we actually have something better now in C++ 11. We can explicitly delete the default constructor so that using it or attempting to use it is actually a compile error. And that's exactly what we want, because now this is the only valid option through which to initialize the class, and we know that every time it'll be given a number of color attachments. So let's move forward and let's create our functions that actually do the work and we'll initialize these textures. So init depth texture, the class should expect to have this called once or 0 times if you don't want a depth texture inside your frame buffer. So what are we going to give it? We're going to tell it width, and we're going to tell it a height, which of course just correlates to how big the texture it should allocate will be. Nothing too fancy there. There's no other parameters that we need because depth textures are, for the most part, all the same. They're very specific in the way that they need to be created, so there's no other functionality that we need there. But as we'll see when we init our color texture, although we still start with our width and height, we will need some additional parameters. In fact, the first one I should have here is not width. What we want to do, because we know that there can be multiple color textures inside of this frame buffer, is that we want the first parameter to specify which one in particular we're actually initializing at this point. So I'm going to use index to specify that. So, for example, if somebody called frame buffer with 2 attachments, the class should expect to have an init texture called twice with excuse me, with 0 passed in once, and then the second time 1 should be the index, and then both will be initialized correctly. So the next thing we want to do is specify some of the initial parameters of these textures. Although a depth texture is easy to create, a color texture can have multiple channels. Maybe you want an alpha channel, maybe you don't. Maybe you want the filtering to be linear, maybe you want it to be nearest, maybe you want the texture to repeat, right? We need to be able to account for those sort of things, and we want to expose that functionalities to the user. So what we're going to have here as our first parameter is the internal format, which is pretty much how many channels we want the texture to have. Then we have our filter, which corresponds to linear or pixel access. And then lastly, we have our wrap, which of course will specify the behavior of accessing the texture past the borders. So after the user calls these 2 functions, or however many of color texture, we want to then check that everything is initialized correctly, right? We don't want to skip that step. We still want to make sure that everything is working. So we're going to have a check FBO function, which will only after everything has been initialized let you know if it's working properly. So you can guess what's coming up next, our usual unload function, just like all the other classes we've created, and that'll clear memory off of the OpenGL memory, off of the video memory for when we're shutting down the program. And I want to make sure that you get these comments in here because the next function is going to have a confusing name, a bit of an ambiguous name maybe. Now, once we start using textures as render targets, you have to make sure that you provide a way to clear them, just like you clear the back buffer at the beginning of every single frame, right? If we see here, the process of drawing a frame always starts with this clear, and the same is true with frame buffers after you've used them to render something. For the next frame, you want to start from scratch, so you want to erase that, at least most of the time. So we should add a clear function, which has the same functionality as clearing the back buffer, which pretty much sets all the attached textures to the clear color, which most of the time will be black. So not to be confused with the unload function that actually deletes the OpenGL objects. Clear is a very valid thing you should be doing every frame. Of course, as with other OpenGL objects, they need to be able to be bound and unbound. So we're going to have a couple functions for that. And next, we're going to have a function that we'll take a look at the end called move to back buffer. So of course you might be asking yourself how all of these frame buffers work because you render stuff to them, but they're not on screen. So you need some method with which to put what you've computed off screen onto the actual screen, onto the actual back buffer for the user to view. So one of the ways to do that, I'll show you the specific OpenGL function for it. It's pretty easy. We'll put it inside here, and it'll allow us to simply copy the location, or rather copy the entire frame buffer into the back buffer without having to create any shaders or anything fancy like that. What we do need to tell it, however, is the width and height of the window we want it to copy to, so that it knows how to do it properly. Next, we're going to provide arguably the most important functionality of the entire class, and that's the ability to retrieve the textures from inside the FBO. So we're going to have a get color handle and a get depth handle, and both of those will return a unsigned integer, which is literally the same unsigned integer that's given to the name of the texture. So after we render to one of these frame buffers, we can take those render targets and bind them as we would any other texture at all, and we can use them in further processing. So one thing you could do if you really wanted to is render your scene, and then you can use that on it as a texture for your model. It looks really funny, and you get this 3D person walking around, and their skin is actually like a camera view of the rest of the scene. It's really cool. You should try it sometime. So we'll see how that works as well. And oops, I made a mistake here. Get color handle will of course need to specify which one, since there might be multiple. Now in terms of the private data, we're going to need to manage our OpenGL objects, and that starts with our FBO itself. I'm going to initialize these to null, but I'm not just going to use 0. This time around, let's be a little bit more specific. Let's use GL none, which is, as you can see, just equal to 0 anyways, but it's more readable. Let's have another GL int, and this is going to be our depth attachment. And then we're going to want our color attachment, but we're not going to want to simply declare it as a regular variable. We're going to want a pointer to it. And essentially what we're going to do is when the class is initialized, we'll allocate this as an array of the appropriate size, because we cannot possibly know ahead of time, as in right now when we're coding, how big we need this to be. So I'll set that to a null pointer. Now lastly, we're going to have a GL enumeration. I'm going to call that buffs. I'm going to set that to null pointer. And I'll explain that one when we get into the CVP and it becomes more obvious as to what its purpose is. Lastly, for our own management purposes, we should just have a straight up int showing us how many color attachments we have, so that we don't go over the bounds of our arrays. And that's all we need. And our header file is ready to go. So next step is to add a CPP, frame buffer. We're going to include framebuffer.h, of course, and let's bring in our functions. Don't need to do anything with the constructor, the default one anyways. That one is just going to be non-existent. Now I can go ahead and open all of these up. Oh, I should add the scopes in first before I move them onto new lines. Scope all these functions with the appropriate first name, you could say. There we go. So let's get started. Up at the top, what we want to do first of all is set our num color attachments equal to the incoming variable. And so now we can actually give some length to our color attachments array. We can create a new GLUint array of num color attachments. And so this array will hold all of our handles for each color texture. Now what we need to do is we need to initialize that buffs variable. So what exactly is buffs? Well, buffs is simply a variable that's going to hold the parameters we need to pass into a function later on. So that parameter list is a little bit tricky to set up every single time, so it's easier to set it up at the very beginning and then just have it as a pre-set up variable of our own that we can give in later. Basically, to jump ahead a little bit, we're going to need to call a function called drawBuffers when we bind the frame buffer itself, and this will tell OpenGL how many of the internal textures we want to be able to draw to. So if we want to draw to 5 different textures, we'd have to put in 5 here, and then we'd have to specify an array of the parameters corresponding to all of those textures. So it's a little bit tricky to set up, and I'll show you how to do it. It's best to do it with this variable here. So first things first, let's initialize it to the right size, and it's going to be a GLEnum of, num attachments, of course. Then we're going to loop through it and set up each element. So buffs at I needs to be set to the color attachment we want to be active. So for instance, if we only have one texture, then this would be it. We'd have a buffs array with only one element, and the thing inside this element would be equal to attachment 0. Here's the problem though. Say we have 3. We would need to set up our buffs array in order to look like this. Color attachment 1, color attachment 2. So how can we do that inside the loop so that we don't have to code it so many times, and so that we have a generic solution? Well, the solution is, if we hover over this, we can see that this is really just a macro that's equal to some value. We can see there it's 8CEO, which is a hexadecimal value. So we can jump to definition by hitting F12 if we have our cursor over it, and we find where it's defined, and we see that all of these in a row actually have incrementing values in hex. So we don't actually need to do anything fancy, like if I equals 1, do this, and if I equals 2, use the next one. That's garbage, right? But because we know that it's just a value, we can simply add I to it, and it'll move to the next ones as required. So that'll be set up for when we want to bind, and this buffs will have one of these color attachment values prepared for every single attachment inside the frame buffer, so we can easily bind all of them and make the entire thing active at once. So let's write a little comment here so we remember. Buffs is required as a parameter for GL draw buffers. So let's move on. Our destructor will simply call unload to clear data from the GPU. And let's get into a more interesting function in a depth texture. So what are we going to do here? First, we want to make changes to the frame buffer. So we're going to bind it by calling bind frame buffer. And we're going to call GL. Whoops. What's my autocomplete doing? Frame buffer. There it goes. GL frame buffer. And we're going to bind our FBO. And oh, I'm silly. I forgot to actually create the FBO. We need to do one more thing in the constructor. And what we want to do is we want to register the FBO. The reason we want to do it in the constructor is because we don't know which of these functions is going to be called first or how many times. So the best way to ensure that it only happens once is to do it in the destructor here. Sorry, the constructor. So as you might expect with other OpenGL objects, there is a gen call. Gen frame buffers, how many? One. Address of the handle. We pass FBO, and it's done. So now our FBO is ready to go, and we know it exists. So after we bind it here, we can go through the step of creating the depth texture. And then after that's done, we can bind it to the frame buffer so that the frame buffer has ownership over that texture and has the ability to draw to it. So creating a texture is actually just the same as creating any other texture. It's only once the texture is bound to the FBO that it gains that additional functionality of being able to be drawn to. So this process is going to seem rather familiar. We gen textures, one. Which one are we going to use? Well, in this case, it's going to be our one depth attachment. Then we want to do stuff to it, so we're going to bind it right away. Bind texture. It's going to be a 2D texture as usual. Texture 2D. Now it's bound. Now we need to actually upload some data to it to make it have a size, but we don't have any data to upload, right? So the one difference is that we're not going to call GL texture data. We're going to call GL text storage. Text storage 2D is essentially the same function except that it doesn't ask you for a pointer to data. All it does is allocate the space inside of OpenGL and your video memory for the texture to exist, but it just leaves it as starting blank. So it's pretty much intended for use with FBOs as opposed to allocating textures for your models, in which case you do want to immediately upload something to them. So the first parameter is the target, the type of texture. It's going to be a texture 2D. Levels, we want 1. We don't want any mapping, but we want one level to exist. So we put in 1. Internal format is going to be something you've probably not seen before. It's specific to depth textures, and it's called depth component. We're going to select 24 because we have a 24-bit depth texture. And width and height are simply going to be the incoming widths and height. Next, what we want to do is make sure that some of these parameters for the texture are exactly what we want them to be. We don't want to leave it up to chance. So let's call GL text parameter I. As usual, we need to specify the type of texture we're talking about, a texture 2D. Let's set first our filters. So there's two of those, right? There's the texture minification filter, min filter. We're going to set that to GL nearest, right? These are pixels we're going to be drawing to and reading from, so we don't want to have linear interpolation going on. We want our rendering and our reading to be spot on pixel by pixel basis. So I'm going to copy and paste that, and I'm going to change the second one to a mag filter, the magnification filter, which is also going to be GL nearest. Then I'm going to set the texture wrapping behavior for SNT or UNV. And that is going to be clamp to edge. Make sure you don't ever use GL clamp anymore. GL clamp is actually deprecated. GL clamp to edge is the one that you should be using. So now the texture exists, and we know it's in the format that we want. It's not going to be anything interesting to the frame buffer until we bind it, of course. So we're going to call GL frame buffer texture 2D, and this function will take, as usual, first the type we're talking about, then what type of texture are we talking about? We're talking about a depth attachment. We want it to fit into the depth attachment slot. Just like there's color attachment slots, and as you can see they are numbered, there is one depth attachment slot. What type of texture is it though? It's a texture 2D. Then of course, what's the texture handle? Depth attachment. And the levels, we don't want it to change anything with that, so we're going to leave that as 0. And then we can just unbind the frame buffer. I'm going to use GL none again instead of 0 to be more readable. And that finishes up the function for us. So after this is called, rendering to this FBO would automatically cause geometry depth to be written into this texture. So a note to be made here is that even if you don't want to read from this depth texture, you will still need it because it's the only way that the FBO would be able to keep track of where objects are in relation to each other. So if you have an FBO that doesn't have a depth texture and you render all your objects at it, you're not guaranteed that the objects that are in front are going to appear in front because that frame buffer cannot keep track of that information. So remember, if you're going to be rendering actual geometry into your frame buffer and not just basic post-processing, it's very likely that you're going to want that depth buffer there in order to keep track of depth on a per pixel basis, so everything ends up looking correct. Now our color function is actually going to look so similar that we might as well start with a copy of our depth texture. We're still going to bind as usual. We're going to create a color texture here instead. So the target of this color texture is going to be color attachments. Oh, that should be an S. It would be more understandable with an S. Let's change that to color attachments. There we go. And up here too. Perfect. Color attachments, it's an array, it's not just one. So let's take color attachments at index. Right, the index coming in, being specified at the beginning. We're going to create a new texture into that slot, then we're going to bind it. And we can still use texture storage in order to create the texture. But we're not going to have depth component as the format anymore. The format now can be, RGB, RGBA, BGR, whatever the user wants. And that's actually coming in through the function call. So we can simply specify that. Now the filter modes, we're no longer going to hard code. That's going to come in from the call. And the wrap mode is also going to come in from the parameter list. Attaching the texture is also going to change just a little bit. We're going to have GL color attachment, and these all go up by value as well, 0, 1, 2, 3, just like the ones from up here. So in order to resolve to the actual attachment that we want at this point in time, we're going to use the same trick of adding index onto it. And of course, make sure we change the last parameter here as well from depth attachment to the current color attachment, and we're done. Check FBO is not going to be too bad. We first bind the frame buffer. Of course, these function calls are probably being called once in a row after one another, but just to be safe, we'll bind and unbind the frame buffer each time to make sure that nobody outside of the class gets a chance to do any fancy stuff and break us. So after the frame buffer is bound, we can call an OpenGL function called check frame buffer status. Very specific function. Would be nice if a lot of other functions were as fitting in their name. So we're going to take the buffer status. What state do we want to check? Well, the regular frame buffer. And this is one of those really nice functions that actually just returns the value. So we check. We have a problem if this is not equal to frame buffer underscore complete. And in that case, we will return false, and we will also unload the incomplete data. Otherwise, we return true. Now for unload itself, we are going to clean up all of the variables we've created, starting with buffs. Again, to make sure we don't accidentally create memory that delete memory that doesn't exist, we're going to make sure we check that they're not equal to null and such. So delete buffs. Make sure we want to use the delete with the brackets because it was called with new that had brackets. It's actually dangerous behavior to call the regular delete on an array of data. And of course, after that, we don't want a dangling pointer, so we set it equal to null. Next, we can start clearing our color attachments. Whoops. We can't delete these right away though. These represent texture handles that we need to release. So the first thing we're going to do is we're going to loop through them. Basic for loop, I less than color attachments. And for each one, we're going to call GL delete textures. How many? Well, one at a time. At the address of color attachments I. Clear all of those textures, and then once all of that is done, we are safe to array delete color attachments away. Setting it equal to null pointer, of course, just as with buffs, and that's cleared up. Depth attachments is a little bit easier because we don't have to take care of a loop. So what we want to check here is not if it's null pointer, but if it's equal to GL none, because this is not a pointer, straight to the GL uint. So what do we do? Call delete textures with the depth attachment as the target to be deleted, and we set depth attachment to GL none. Lastly, after all of this has been done, we can set num color attachments back to 0. Now clearing is the different process of making sure all the buffers are completely zeroed or otherwise set to the clear color. What we're going to want to do is create a bit field, and we're going to add to this bit field the parameters that we actually need to clear. So let's start this at a value of 0. Using 0x, 0 here gives us a hexadecimal equivalent of 0. If we want, actually, we can just have a regular 0. It's no difference. So what are we actually going to be doing here? We're actually going to be creating this parameter. So just like we call GL clear on anything else, we're going to need to specify if we want color to be cleared and if we want depth to be cleared. Now, of course, with the back buffer, we know there's a color and we know there's depth, but our frame buffer might have one or the other, or both. So we need to dynamically create that parameter. So if depth attachment does not equal GL null, none, then we can add the GL depth buffer bit onto temp. This here is a bitwise OR operator, so the bits inside of temp are going to be ORed with the bits inside of this, and the result is going to be written back into temp. So essentially, if you look at this bit here, you can see that there's only one bit that it will actually be set in that value, in that hex value. So each of these buffer bits, if we take a look at GL color buffer bit for a moment, we'll see that it sets a different location entirely. And so we know that by ORing them together, we're not overlapping or losing any of these bits. And inside of OpenGL, they simply check, hey, is the 7th bit 1? If so, then they probably wanted the buffer bit to be clear. Or is this 3rd bit 1? If so, then they must have also had the color buffer bit. So by ORing them together, we can actually compact all of this data into one memory space and then send that off to OpenGL. That's why we use the that format with the bitwise OR. So here what we're going to do is we're going to also check if color attachments does not equal null pointer. And if so, we do a similar process. And so what we've done here is similar to the idea with buffs. We've created a variable that we need to pass in as a parameter ahead of time. The reason buffs is all the way back here in the constructor is because it is dynamically allocating memory, and that's not something that you want to do needlessly. That's a much heavier operation, so it's worth our time to move that back. However, this is not nearly as heavy, so we can throw that in here for simplicity. Now, in order to bind the buffer, we need to actually make sure it's in order to clear the buffer, we need to make sure it's bound. So we bind frame buffer, GL underscore frame buffer with FBO as the handle. Then we call GL clear, and we can pass the temp variable in. And lastly, we remove the frame buffer. We unbind it by calling bind with GL none. So this clear function is actually the exact same one that we used in main. But since the frame buffer is bound, of course, its behavior will be a little bit different. So to finish up, bind is going to be pretty straightforward. First, we bind the FBO itself, but then additionally, one last step is to call GL draw buffers, which doesn't actually draw anything like GL draw arrays, so don't get confused about that. GL draw buffers simply allows you to activate the color buffers inside of the FBO that you want to be valid for drawing. So it is possible to have an FBO with 10 textures and then to activate only 5 of them at a time to draw to those, if that's the case, that if your game calls for that case. So for our bind function, we're simply going to activate all of them. So we're going to say num color attachments, and then we're going to pass buffs which specifies exactly which ones. So it wants, the function call itself, as you can see, wants an array to a GL enum, and that's exactly what we've provided it. And it'll find color attachment 0, 1, 2, 3, up until however many we have. So notice we don't have to tell it to draw to the def buffer. That will actually happen implicitly. As long as a def buffer exists in the FBO, any geometry being thrown at the FBO will also write to the depth, given that def buffer writing in general as the global OpenGL state is enabled, which it usually is. Unbinding is even easier. We simply call GL frame buffer with none. Moving to back buffer now is a process that would be pretty difficult if it wasn't for some built-in functionality. So we're going to call bind buffer, but we're not going to specify GL frame buffer this time. We're going to specify GL underscore read underscore frame buffer. We're actually going to bind two things here. So to the read buffer, we're going to bind the FBO, and to the draw buffer, we're going to bind GL none. That is to say, we're going to bind the back buffer. So we're setting up here for the function call that actually moves data, but it wants to know where am I moving from, the read, and what am I moving to, the read. And that function is called GL blit frame buffer. It will essentially move data for us. So what it wants to know is simply the rectangles inside the source and the destination that we want to draw to and read from. So our source is going to be starting at 0, 0 as our bottom left corner, and then moving forward to window width and window height. And then our destination as well, we're going to have be the entire thing. Next, it wants to know what it wants to actually copy. You can specify the depth, or you can specify the color. If you specify the color, it'll take the first texture in there and it'll move it to the frame buffer, to the back buffer. And lastly, it wants to know if these two rectangles aren't the same in size, and I have to scale up or I have to scale down, should I use linear sampling and interpolate between pixels, or should I just go for the nearest pixel? Now in our case, we know it's hard-coded to always be the same size. So calling this function with linear sampling won't make a difference. So we're going to specify nearest to make sure that we get those crisp pixels that we initially rendered to begin with. We don't want to lose any of our information. And so what I'm going to do to unbind is I'm going to call GL none on top of GL frame buffer without read or draw. GL frame buffer on its own like this entire time has actually specified both the read and the draw buffer at the same time. So calling this function is actually the same as calling these two functions. There are actually two different slots that you can bind to, and GL frame buffer does both at the same time. So that's why we don't need to have two lines to unbind what we bound. Now these last two functions are the simplest. Depth handle, return depth attachment, get color handle, return color attachments at index. I'll leave it up to you, the class, to add the necessary error checking here to make sure that we don't go over the bounds of the array and that this array exists to begin with. That's obviously something you should do. Most of the time in our coding in these videos, we've avoided that kind of generic error checking just for the purposes of speed, but I do expect that you've been putting those in your own time, especially if you're actually using this framework for your GTW games. So at this point, we can go ahead and we can go to the game class and start using this thing. So let's first at the top include our new frame buffer class. Down next to our objects, we'll create a new frame buffer. I'll call it our main buffer. Once I've created this as part of the class, an issue is going to arise which won't let us to compile. And if we scroll up to the top of game.cpp, we'll see exactly what it is. The default constructor of frame buffer cannot be referenced. It is a deleted function. So why are we getting this error here, right? We're not even in the frame buffer class. Well, what's happening is the game class, as it tries to construct itself and allocate enough memory for itself in order to exist, it realizes in order to know how much memory I need to know how much memory the parts of me need. So it creates default program and it knows how big a space that needs. It creates monkey. It knows how big a space that needs. Creates grass texture. Okay, it knows what to do. Goes to main buffer and it realizes there's a problem. It says main buffer doesn't actually have a default constructor. I don't know how this object actually wants to set itself up. I can't do it. So because of the fact that main buffer doesn't have a default constructor, and we've put it in the game class, now the game itself cannot construct either. And that's why we're getting this error all the way up here. Now the solution is to call the function that we actually want to be induced, which is the frame buffer constructor that has a parameter. So of course this is actually what we want. We want this error to occur because we didn't want people to be able to accidentally create a frame buffer object without specifying that value. So what we're going to do is we're going to specify in an initializer list that we want our main buffer to contain one color buffer. By calling this constructor in the initializer list, we guarantee through the specification of C++ that this occurs before the brackets of the constructor starts, and in turn that allows the game class the chance to fully initialize itself and all of its parts before any of its code is executed. And that makes it happy, and now it's comfortable knowing that it can set up its own memory completely and correctly before it ever has to get used in any way. So with that done, we have our main buffer set up and it knows how many colors it wants. We just need to initialize it. So the first thing we're going to do is we're going to set up its color handle. Sorry, its depth handle. Oh, what am I talking about? We're going to init its depth handle. And the parameters are going to be pretty straightforward. We just tell it the same as our current window's width and height. Next, we want to call init color texture, and we know that we only have to call this once. Index refers to, of course, again, which color texture we want to do. There's only one, so we specify 0. Next is width and height, same as the window. Then we're asked for the internal format. What we're going to specify here is GL_RGBA8. This will tell the texture to create 4 channels and give each of them 8 bytes. Filter mode, we're going to be drawing to the screen, and we're always going to be using this texture in the full screen. So there's no point in having any sort of filtering going on. We're either going to be drawing to it as if it is the full screen, or we're going to be moving it onto the full screen. So we know we're never going to encounter a case where we need to treat it as though it's smaller than it is, or scale it up, or anything weird like that. So GL nearest is fine for us. GL clamp to edge will also do the trick for wrap modes. And now that both of the buffers are set up, we can call inside an if statement our check FBO function. So if not check FBO, we can output an error message. I'll just steal one from up here. And we can say FBO failed to initialize. Pause and exit. And that's all it takes. And so of course, adding another texture to this is as easy as setting the constructor to 2 and copying a new call here with index 1. And of course, the second texture can have entirely different parameters. It can have a different size. It can have a different data format, different everything. And later in following weeks, we'll see some cases of that. But for now, let's stick with the 1. So how do we utilize this now, right? Because we're still rendering to the back buffer. And it turns out that after all this work we've done, it's actually incredibly easy to use this object. We just take it and we bind it. And just like anything else in OpenGL, the fact that we've bound the object means we've answered one of those key 3 questions that we've talked to in class. When we bind a program, a shader program, we answer the question of how do you want things to be rendered. When we bind an object, we answer the question of what do we want to render. When we bind a texture, we also answer how we want to render things. We give it the proper data. So now we're answering the final question of where do we want to render. And simply binding the frame buffer does the trick. So like this, if we run the program, we'll actually find that we don't get anything on screen anymore. And that's perfectly normal because we're rendering to an off-screen location. So let's take a look in Nsight and find out what's going on. And before we do that, let's go to the top and do the thing that I forgot to do, which is to add the clear of the frame buffer next to the clear of the rest of the frames. So at the beginning of each draw call, all our data across the back buffer and all FBOs is going to be cleared. You might not always want to do this, but for this buffer we will. So again, if I run, nothing is going to happen. We won't see anything. But if I run with Nsight, and I start graphics debugging, I can prove to you that that render still exists. So if I capture a frame here, we can see the 2 clear events. There's a second one now. And at the end, we can see that absolutely at one point, look at that, our monkey exists. Well, it exists, but it exists nowhere that we can actually see it, so it doesn't really matter. So let's move it onto the back buffer. We can do that quite simply by going at the end of all of this and calling main buffer dot move to back buffer. And the parameters for that, of course, will be the dimensions of the window width and window height. And that'll ensure inside, as we've seen, that the correct buffers are bound for the move to take place. If I run it now, we'll see once again in our back buffer. So if I take a look at Nsight, there'll be an additional event now. There'll be the 2 clears, then the draw, and then we can see the GL blit frame buffer come up as the move. So there is one issue with all of this, right? Which is that if we were going to just do this, why didn't we just render it to the back buffer to begin with, right? But the idea is you complete all of your rendering off screen in order to give you the functionality to add layers. And then your very last post-process effect actually sets its target as the regular back buffer. So you save yourself the step of having to call the move in the first place, and you're able to kill two birds with one stone because your last render both applies a post-process effect and moves all your data to the back buffer where the user can see it. So before we finish up today, let's add our first post-processing effect to this project, and let's use it to efficiently move our off-screen target back onto the frame buffer. So what I'm going to do now that we're going to start playing around with more and more shaders is I'm going to right-click on the project. I'm going to add a new filter. I'm going to call it shaders. And from our, well, actually I can just right-click it, add existing item. I'm going to find our shaders, and I'm going to put them into here so that now we can always just double-click these to make them come up. I'm going to go into the folder though. I'm going to copy and paste, and then I'm going to rename the copies to grayscale post. So what we're going to have here is we're going to create a post-processing effect that takes the input image and then converts it into the grayscale equivalent. So let's go back into our shaders. Let's add these two new ones, and let's edit them to be a little bit more appropriate. Or you know what? Let's actually do something else first. Let's talk about one of the functions that we'll need to get these shaders to work before we actually start working inside of them themselves. So when we start talking about post-processing effects, as we've seen in class, one of the most important pieces of functionality to have is the ability to draw a full screen quad in order to efficiently make sure that fragment shaders appear on every single pixel of the screen. That's all we want to do. By drawing that quad, we're doing nothing else but focusing on the fragment shader part of the pipeline where we can actually do all our work in our fragment shaders. So in order to do that, the easiest way is to just simply create a VBO that has the correct parameters inside of it to draw that frame buffer. So let's do that. Then we can just call the VBO, bind it, and draw it whenever we need to. So let's create a new header file. Let's call it utilities. Inside of utilities, we're going to pragma once and define two functions: init full screen quad and draw full screen quad. So of course this is not very interesting at all. Let's open up the source file. Let's create a source file rather. Utilities. Include utilities.h, and it's in here where we're going to set up these buffers. So first thing we're going to need is to include glue.h. We're going to need GL functionality in here. Next, we're going to need to define the same buffer offset that we've had before in order to avoid that compiler error, the warning. So that's simply going to look like this. Simply a macro that takes our I and really does absolutely nothing to it, but adds it to a null pointer in order to essentially get the pointer equivalent of what that value would have been, which makes the OpenGL function call happy. Now we're going to need two variables in here, and we're going to need a full screen quad VAO, set that equal to GL none at first, and we'll need a full screen quad VBO. And now both of these variables existing here will keep track of the values Even though we don't have a class, it doesn't matter, they still work. So the init quad will essentially create a VBO just as we've seen before, except we're not going to be loading in the vertices or the texture coordinates from file. We're just going to create them programmatically because they're always going to be the same and it's not going to be too big. So the first thing we're going to do here is we're going to create a float array VBO data. We're going to set it equal to a lot of stuff. What's it complaining about? Oh, it's complaining because I haven't filled it in yet. So essentially what we're doing here is we're going to literally be typing out the VBO that we're going to be sending. So first things first, we're going to have a whole bunch of sections in 3. This is going to be one triangle, right? X, Y, Z for each vertex. I'll separate the second triangle, X, Y, Z for each vertex. And that's all we need, right? That and the texture coordinates. So the full screen quad is only 2 triangles. We don't need any more than that. The VBO is going to contain both the triangles as the actual vertex data and the UV coordinates required all in one go. So it's just a matter of setting these values to the right things. First, we're going to do -1, -1. Now the z's never change. The z value never changes because none of the vertices in the triangle move further or closer away from the camera. We're literally setting these equal to the extents of the unit cube in order to jump straight to NDC as we've seen in class and render the correct triangle. So we've seen it in class, so take my word for it that these values work out. Working them out is just monkey work, right? So we're not really going to learn anything by looking at it in detail. But just make sure that yours looks the same as mine. So next, we're going to want to, you've guessed it, gen vertex arrays. I'm going to create one of those, and that's going to go into our full screen VAO. Then we're going to bind it. Vertex attrib array. That'll keep track of all these settings we're going to throw into the VBO. We're going to need to enable the slots, of course, the attribute slots for both the vertices and the UV coordinates. So we're going to call GL enable vertex attrib array with 0. And again with the value 1. Let's mark those down so they're more readable. Then we can go ahead and begin creating our VBO itself. This process hopefully has become pretty familiar to you by now. After we bind the buffer, after we gen the buffer, I gave it away, we bind the buffer. Then we throw the data at it using GL buffer data. Oops, I'm missing the first element here, GL array buffer. Now, inside of the buffer data, we're going to want to specify the actual size of the array, right? So I'd like to separate that out just so it's a little bit more readable. Why not, right? Let's create them here. So let's have an int vertex size. Let's have size, actually let's start this way. So how many vertices are we going to have? Well, there's going to be 6 of them because there's 2 triangles, right? But each of them is also going to have 3 floats inside. And each of those floats is going to have the amount of bytes returned by this operator, the size of operator. So let's have a text coord size as well. It's going to be just about the same, except for every one of the 6 points, there's only going to be 2 elements, a U and a V. So now the size of our buffer becomes trivial. It's simply our vertex size plus our text coord size. The data is a straight up pointer to the VBO data, and I would like to mention that the size of this is automatically determined by this array, so I didn't need to put anything in here. If I hover over, you can see it's automatically filled in as 30. And I can finish this up by calling static draw. Now, of course, I need to properly feed this data into whatever shaders are being bound when there is a render, so I will call GL vertex attrib pointer in order to make that connection between the VBO and the shader. So I will cast this to a GLUint to be sure. So for index 0 for vertices, we're going to be passing in 3 at a time, right? X, Y, Z, 3 floats. The types themselves are going to be GL float. We do not want OpenGL to be normalizing these values behind our back. We set them up just the way we want them. We don't want any stride. This is an interleaved data, although they do exist in the same buffer. Our buffer offset for vertices is going to be 0 because of the fact that they start right at the beginning of the VBO themselves. Now when I copy this over for texture coordinates, I want to make sure to switch this over to index 1. I want to specify that there's just 2 floats. And buffer offset is actually going to change this time to vertex size because the UVs don't start at the beginning of the array, but they start after vertex size amount of bytes. With that, our buffers are all set up and good to go. So we can call GL array buffer with GL none in order to close that. And then we can close our vertex array, or rather I should say we can unbind our vertex array. So absolutely we can create the data in the source code, right? It doesn't matter where it came from, as long as it goes where it needs to. And drawing the full screen quad, because of the VAO, is a trivial process. We simply bind it, we draw, and we unbind it. And apparently I'm very lazy today. I've been copying so much code around. So what do we want to draw? We're going to draw triangles. We're going to start at 0, so we don't want to skip into the buffer at any weird point, but we're going to draw 6 of them. And that's all we need to do. Now our full screen buffer is ready to go, and post-processing will literally be a breeze with these 2 functions available to us. So let's go into game.cpp. Let's include our new utilities file. And inside our initialized game, we can init our full screen quad. And now the only thing left to change is, well, our draw, but we also need a new shader, right? So let's set up what the code would look like, and then we can get the shaders to work with it. So we don't need this main buffer moving to back buffer anymore. Don't want that happening manually. That's wasting its time, right? It's moving, but it's not doing anything to the data as it's moving. So what we're going to do instead is we're going to end up binding our new shader. Then we're going to draw full screen quad. And we're also going to want to bind the appropriate texture. So before the screen is drawn to our shader, we're going to bind the appropriate texture. So we're going to bind a texture, GL texture 2D. Which texture are we going to bind? Well, we're going to grab from the main buffer the texture handle to color 0. So as far as OpenGL is concerned, this texture could have come from literally anywhere. It's just by coincidence that it's also the one that during the exact same frame we drew something to. Of course, after we do finish drawing, we'll want to make sure to unbind that texture. So now all that's left to do is the shader. So let's take a look at what that's going to look like. Let's bring it up in Visual Studio. Things are going to be a lot simpler here in the vertex shader. We don't need any of these matrices anymore because all of the vertices coming in are straight into, they're ahead of their time, right? They're already in NDC. So this becomes extremely simple. We simply take our vertex and we pass it straight into GL position. We can get rid of this. We can even get rid of that. We're not going to have this pose anymore. We're not going to have normal. We're not going to have the incoming normal. The only thing outgoing now is the texture coordinate. So we've actually jumped ahead in the mathematical pipeline, right? Because the incoming vertices are already in normalized device coordinates. And the fact that the W component is going to be 1 when it's written to GL position means that the perspective divide that takes place soon after the vertex shader, in which the 3 component vector is divided by W, that divide won't actually change anything, right? Because it's just 1. So we know that this vertex is going to be intact all the way until it gets to the screen. So when we get to the fragment shader, we know that we've drawn a perfect full screen quad, and we'll see that in Nsight when all of this is done as well. So in terms of the fragment shader, we can get rid of all this stuff. We only need the sampler texture and the incoming texture coordinate. Of course, we still need to just to write to this output color. We can get rid of all of these innards. It's going to look a lot simpler now. Here's what I'd like to do. First, I'd like to read from the source texture. So I'm going to define a new variable here for myself to work with. And it's going to read from texture. The sampler is going to use is utex. And it's going to sample at the texture coordinate, which will correspond with exactly the same location that this fragment is on the screen. So we're going to be reading from the same pixel that was where we're going to draw to as well. Now, of course, we're not going to be drawing to the same location. We're going to be reading from the pixel in the frame buffer and drawing to the back buffer, but the locations of the pixel will be exactly the same. So we know that there won't be any warping to the file. So if we want to calculate grayscale, essentially what we want to do is calculate the average, right? Some average of the incoming color, and we want to write that to outColor. So it would look like this. So outColor would be equal to a vector in which every component has to be the same, right? If it wasn't, it wouldn't be grayscale. We'd have color. Alpha, of course, we can set to just 1 to be safe. So the question is, of course, how do we compute this average? We could simply take the length of the vector, or we could just add them all up and divide by 3. But there's actually a better way. It turns out that the human eye doesn't perceive every single color with the same exact amount of intensity. So in order to get the same grayscale effect that you would from one of those old movies, you'd want to actually use these magical weightings that I'm going to present to you now. So 0.2989 for red, and we're going to add 0.587 for green, and then 0.114 for blue. And now those add up to 1, so we know we're not overly scaling the color up or down. But we've now simplified the color into a grayscale, right? So the last step is to hop into what's it called? Game.h. And let's create a new shader program for this. So grayscale post. It's our post process. We can hop into game.cpp. And just like we loaded our other shader, we can load our grayscale post. And of course, the names we want to use are grayscale post.frag and .vert. And we go down to our draw, and now at the end here, where we should add a comment saying that we're moving data to the back buffer at the same time as our last post process. So we're going to bind that post-processing shader. We do have one uniform to send, which is the sampler for the texture. We're going to simply send a 0 for that, because we want to talk about the slots again, right? Remember from the last video? This is the slot we want to use. So because we're not using multi-texturing, we can simply put in 0. Then after all that's said and done, we can make sure to unbind the shader here. And after we give this a run, we'll find that now our image is in grayscale, which is awesome. So let's take a look at Insight and convince ourselves that this is working exactly as I've explained it. So if we capture a frame here, we can see the right amount of events. So both the black buffer and the frame buffer get cleared. Then we jump over to here and we see that there is a point inside of the frame where the monkey exists with color. And that is, of course, if you see up here, oh, if I move my mouse over it, it disappears. If you see up here, FBO attachment, right? Color 0, we're inside the FBO now. And if I move to the last frame and I enable the wireframe again, you can see the geometry that was rendered is actually a full screen quad. And here we can prove to ourselves that it did in fact cover the entire screen as intended. And of course we can see that the result was a grayscale image. Another interesting thing to note is take a look at the source texture, right? The currently used texture inside the shader is actually the previous render call. It's the colored version of the monkey. That window, which previously showed that the current texture was the grass, shows us that in fact we are using our previous render and simply doing things to that texture. So we're now into the real meat of the course. We can start progressing with some really interesting effects. Our framework is done and is enough to get you through this year and most of next year as well. I hope to see some really awesome post-processing effects coming from you guys and gals. And I'd really like to see some of those homework questions coming through too, especially now that pretty much every single one of them can be completed with this framework. So I hope you liked the video. I'll see you guys in class and have a good week.